Here's an example question. A straight horizontal wire carries a current of 50 amps from west to east in a region between the poles of a large electromagnet which provides a horizontal magnetic field towards northeast of 45 degrees north of east with magnitude 1.2 Tesla. Find the magnitude and direction of the force on a 1 meter section of wire. So here in this plane, lying in this plane, is we have an electric field going in this direction, and also lying in this plane we have a magnetic force which is uniform, and the field lines are going in this direction. So the solution for the magnitude using angle theta between the direction of current and field of 45 degrees we obtain using F equals ILB sine theta. F equals 50 amps, so that's that. L 1 meter, and B is 1.2 Tesla, and then we've got sine 45. So we end up with 42.4 newtons. So that's the magnitude of the force. The direction of the force is perpendicular to the plane of the current and the field and the magnetic field, both of which lie in the horizontal planes. Thus the force must be along the vertical, so the force is somewhere along this vertical, either in or out. Right hand rule shows that it is vertically upward. Basically what we're going to do is we're going to be using F equals IL cross B. So if we think of it as a right-handed screw, if we turn the right-handed screw from here that way, in other words from here that way, then obviously the component, the direction of the force is in my thumb, yeah. So it's going up. So the same with the screw. If we're turning the screw, then we're undoing, if you like. So it's going out this way. The right-hand rule shows that it's vertically upward. Alternatively, we can use a coordinate system with x-axis pointing east, the y-axis north, and the z-axis up. Then we have the vector L equals, so we can work out the vector L then as 1 meter in the I direction. So we're going to use this as the x, that's 1 meter in the I. So we've got our vector L, so that's our vector L got. And our vector B is 1.2 Tesla cosine 45 I. So that's the component of in the I direction, and then the component in the obviously we're multiplying that by the B. So the component in the J direction is sine 45 1.2 T. So then we've got the B vector now, and so if we do IL cross B, we've got B and L, so we can do the cross product. Remember, using the matrix determinant, and then we find we've got the sign. You know, it's not minus, it's plus. So it's plus 42.4 newtons in the K direction. So that tells us that it's going this way, in exactly the same as we worked it out using our geometrical way. Yeah. So by using vectors, we actually get the sign here just by calculation. Yeah. So that's the two ways of doing this. It's always worth doing it both ways like this, because this if we do it using the vectors, using the cross product, finding this vector, finding that vector, and then crossing them using the trick with the matrix determinant, we can always get the sign. Remember, that's really useful check. So do it the geometrical way here first by using, you know, the right hand rules that you know, and then as a check, if it's easy enough, just generate the vectors, work out what the vectors are, and you can prove it with here. So that's that.